Start recording.
Right.
It's done.
Yeah. Yes.
Share screen.
There is this tutorial 13 of this NPTEL course. Yeah. So I think we can start discussing what we aimed at. Yeah.
I'm just sharing my screen.
Sure. Yeah.
See it now. Yeah. So came across this paper. Coupling PD with SPH.
Okay.
So to do FSI.
Okay. Yeah.
This is one of the applications. This is
I
one of
see.
the easiest way to get into period dynamics, if you ask me. This is published by Shanghai.
Shanghai
in
University. Yes.
ocean engineering.
I see.
And if you just cut to the examples first, like what kind of problems they usually handle, it will give us an idea like how to do this. So you have this water,
Yeah.
This one, and it will flow and hits the structure, and the structure will deform. Okay.
Okay, so it's like it's like some dam breaking, huh? Like
so dam
or
breaks.
some yes, and then
correct. So it hits the structure. You can see the structure deforming, right?
Yeah.
Look at this. See the structure deforming, right?
Right. Yeah.
This is something we are interested in doing. So, with the PySPHD, PySPHD approach, the fluid is modeled using SPH. Okay.
Yeah.
If you go for the numerical techniques now. So, so SPH is used for fluid. Okay.
Yeah.
These are the equations. One.
Okay.
This is the equation fluid. Some numerical method technique.
Yes,
That's
I
it.
see.
And for structure, elastic structure, you have period dynamics. Okay. So in the last lecture, we have discussed how to do the period dynamics for structure, right? We were this bond based, and some state based models we have discussed. So, but here he uses just a moment. Okay, he uses bond based for the structure. So if you observe, so you have the horizon. I have read it actually. Your horizon, you have these neighboring points, and each point is connected to some, like it is connected to all these points, and you have to literally save those initial bond distances. This is the initial bond distance. So zeta here.
Yeah.
Write it. Yeah, right.
Which app is this? Just asking.
Some app, man. Yeah.
Which one?
I think this is PDF viewer.
Okay, PDF viewer. It's free of cost, huh?
Yes.
Okay.
They're good as well. So if you look here, so I heard that first state-based dynamics was proposed. No, that's what I heard first. First one is this. Yeah. So first it was state-based, then the bond-based is proposed. Okay. Also in state-based, so I seen that what is the difference between the state-based and bond-based is in state-based, which was proposed first. There you have to have equal and opposite forces. Okay.
Yeah.
So you have these points right here. If you look, you have these points right. So while computing the forces, what you do is for I in range of I points for J in horizon, right?
Yeah.
You do that. The point is, say that you are applying force on I due to J, okay? And that is so. But in state-based system, you'll also apply force on J due to I. But in bond-based,
J due to I. On J due to I.
so
Okay.
like both will influence both the particles
Both ways.
in,
Okay. Yeah.
in state-based. But in bond-based, I have read literature. It states that J may apply force on I, but there is no rule that I should apply on J as well. That's why they have invented this bond-based model.
Okay. J is on I, but I may not on J. Huh?
Just while computing the force. That's what I've seen. So we have to do some.
Okay. The thing is that the reason being is because we should not count the same thing twice, right?
Not twice. No, it's not like that. Say that you have solar system, okay?
Okay.
Sun. I don't know what comes next, but Earth comes that.
Yeah. Sun, Mercury, Venus, then Earth. Yeah.
Sorry. Sun, Mercury, Venus, and Earth. Okay. So you're computing force on Venus. Sorry, Mercury, not Venus. It's Mercury, no? First is Mercury, no?
Yeah, first is Mercury.
Sun, Mercury, Venus, Earth. Okay. So you're trying to compute force on Mercury. Okay. So what you will consider? You'll consider. Say only we have 4 planets. Okay. You will consider Sun. Consider Venus, right? And also Earth. So say this is I. But while computing a force on J, which is Earth, so in state based, you will consider both. Like M will consider E and E will consider M. But in bond based, E may not consider M.
Could you please repeat this part? Yeah.
Okay. So what I'm trying to say is, so you're computing force on M, dude.
Okay, force M on?
Force on M due to all the other planets and the star.
Okay, fine, yeah.
Okay, so in state based, you'll consider Earth, Venus, and Sun to compute force on Mars. Okay, also while computing force on Venus, you'll consider Earth, Mars, and Sun. So each one will also have influence on every other point.
But just on one side, you mean, huh?
On both sides.
Okay. Immediate neighborhoods, huh?
Immediate, but also you'll have. Oh, I'm trying to say that. I'll just it's much better.
Yeah.
Yeah. So you have several points too. Okay. In period dynamics, you have several points, right?
Okay.
So you have this horizon. Okay. We have two, right? We have state based and we have bond based.
Yeah.
Okay. Forget about bond based for some time. There's only state based. State based. So you have this circle, no? Each one will have a horizon, right?
Okay.
Okay. So there you have particle I here. So you have 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now we're computing force on particle 1. So if you draw the horizon, it will be like this. Okay.
Okay, yeah, there is the horizon. Yes.
Right. So how will you compute the force on I for J in horizon delta of particle 1, right? So what are the particles in this? What is this? Is equal to 5, 7, 2, and 3, right?
Yeah, 5, 7.
Do you understand
2,
that?
3. Yes. 5, 7, 2, 3. Right. Yeah. This falls within the horizon. Yes.
Okay. Then what you'll do? You'll add force on 1 plus equal to some coefficient times W times some bond length between 1 and J, right? Do you follow this equation?
Yeah. So this second one is F plus all the members
Plus
which
equal
are
to. Plus equal to. I mean,
okay. You're summing over all those members along with the weights, corresponding
something,
weights.
some expression. Yeah. Some
Okay.
expression.
Yeah. So
Okay.
you are just using that Kronecker delta, right, to say that whether
it's not Kronecker delta. It's actually
no, the second one
bond.
In the second line. Yeah. So we are okay. So we are what you call doing some bond distance, right?
This is
Between
bond. This is not Kronecker delta. This is
sorry.
B.
Okay. So bond distance between 1 and the its neighbors.
1 and J, because I'm only finding forces on 1.
Right. And lambda delta 1 is just the collection of the set of neighbors belonging to A. Yes. Okay.
Now, to compute forces on all the particles, what you'll do for I. I in range. I'm erasing this.
Okay.
All the particles. So how many particles do you have? 1, 2, 8.
And this has to be done for okay.
To compute forces on all the particles, right? Like
right. Yeah.
Then we will do horizon of
I. Yes.
Right? And here what we'll do? We'll do f of I.
Right.
And here also we'll have I.
Yeah.
So, but the point here I'm trying to say here is in state based. Okay. Say you have this horizon. Now take the horizon of 2. Okay. What will the horizon of 2? It will be something like this. Correct? So in the horizon of 1 we have 2.
Yeah.
Similarly in the horizon of 2 we have 1.
Okay. Right? 2 is in horizon. Yeah. Okay. So 3 is like common to both of them, right?
Common to both. So leave 3 for some time. Okay. Similarly, when you take 1, 3 is in the horizon of 1. Right. So while you're computing the force on 3 now, 1 will also be in the horizon of 3.
Right. Yeah. Of course. Yes.
Okay. So there will be like, see, it's like when you go to space now. 2 astronauts say they push each other. They both will go back now because equal and opposite forces are acting.
Yes. Exactly.
Momentum is conserved, right? Similarly, here also, if 3 is applying force on 1, 1 will also apply force on 3 and is equal and opposite.
Okay. Yes.
And should write properly. This is in state based. But in bond based, there is no rule that if 3 is acting force on 1. Okay.
3 is acting on 1, yes.
Then there's no rule that 1 is also acting on 3.
Okay.
That's what the difference between state based and bond based.
I see. Yeah.
I will share it. Teams. Look at this. Yeah. In order to distinguish between the new formulation. So the original is bond based.
Yeah. Yes.
So the new formulation is state. Okay. So whatever I discussed is actually bond based. Okay. So in the new one is state based. Is the interaction forces
do not need to be
equal and opposite. You see? You understand?
Okay. So this is more general, right?
I don't know if how to. I don't know how to say general and everything, but
because the thing is then bond based will be a special case of state based, right? Because need not be
state based. So in state based we don't have equal and opposite, but in bond based we have equal and opposite.
Yes.
I don't know which one is superior. I don't know.
No, the thing is state based is superior because the thing is it said need not be, so there is no requirement per se. If it is there, it's fine.
Okay.
Yeah.
Yeah. That's true.
Yeah.
But you understand
just-
the point, right? What I'm trying to say,
Yeah,
like
yeah.
equal
Yes,
and opposite
yes.
and everything.
Mm-hmm. Okay, so it can handle asymmetricity, right? In the force system, in the force mechanism, right? So, like, although you are what do you call influencing other body in one manner, the other body need not influence you in the same manner, right?
Correct. That's what he says. But the point is,
Yes.
it essentially breaks so many physical laws because, say, you are in.
Yeah.
Of course, right? Because in stress, while we are deriving stress in our control mechanics course.
So in this
we
case,
have
the
said-
stress matrix, if it, I mean, the thing is, Perry dynamics doesn't have stress matrix, but say if it were
Yeah.
existing, then it would not be symmetric.
Correct. It is wrong. No. That's
Yeah.
what, because in stress while you derived in our class, one of the tutorial classes.
Huh.
Discuss that it is equal and opposite. Like we have discussed all that stuff.
Right.
But here, if this is the case, then the other block, other cubical block, won't apply the same force or equal and opposite force on the adjacent cubical block, right? So that's what. But I don't know what they mean by this. And so you have to investigate a little bit more about the physical validity and the applications they are doing for the state-based. But the point is, first is bond-based, which is symmetric and everything.
Right. Yeah.
Second one is state-based. So here I have to flip it. So here, this is bond-based, and this is state-based.
Okay. Yeah.
First is bond proposed. Second is state. Okay. Going back to the paper. So if you look at this, yeah. So here, this is how we compute the force.
Exactly. Yes.
You understand, right? So it's like the horizon. So you're applying the force on particle I. Okay. And you loop over all the particles of that particle I.
That is, yeah, within that.
Compute the force using this F.
Right.
This force density, as we have seen from the yesterday like last meeting, is force density because you're multiplying by the volume, right?
I see.
You remember the MATLAB code?
Yeah.
And
so it was what you call as force density, right?
Correct. And the force density is computed using this equation. What is this? Say that you have. So you have initially block.
Yeah.
So you have some block like this. 1, 2, 3, 4, 5, 6, 7, 8, 16. You're trying to find the force on this particle, say. Okay. So after the deformation, let's say we'll take these 3 9 points. After the deformation, say it becomes something like this. Trying to find the force on this. So these are the neighborhoods of the particle. Okay. So now initially, so the zeta here, if you observe, this S which you wrote is computed like this.
Yeah. That's what bond stretch ratio is.
Correct. That's right.
Yeah.
So I think
this is just like the longitudinal strain that we look, right?
Exactly. Yes. So initially you know the distance. After the deformation, you know the distance. So from this strength, you will compute the S value. And mu is a constant. C can also be computed from the microelastic modulus. I think it's given somewhere, or it's not given here, but yeah, it can be computed from the given geometry. Okay. And we can simply find the force. Once we know the force, simply use the velocity wallet scheme or any other scheme to move the particles. That's the pre-dynamics algorithm. But the question to ask here, one of the important questions to ask here is, say that these are deforming, the particles are deforming like this. Will the neighbors stay the same all the time? You understand my question?
Okay.
The neighbors, will they move? Like if say that say that you have this one-dimensional period dynamics problem.
Yeah.
Okay.
Mm-hmm.
Computing force on this. At time t equal to 0, this is the horizon. I would say this is the horizon. Okay. Equal to 0. After some time, say it deformed and it became too far away.
Right.
Since our horizon is always constant, no, like maybe 0.1 meter or something like that. If I again take the horizon, then only these 2 points will come in the horizon.
Okay. So the thing. So okay. Okay, so we cannot have a constant this horizon also, right?
I don't know. That's what I'm asking. So like we don't know. So you have to see some more literature, or you have to read upon it to know that if what is the case. So if we figure it out, then we are actually done. So the only part which is left to at least to simulate this 2023 July paper on period dynamics is we know neta, we know zeta, we know this. Okay. We know S value also. We know mu also. We just have to know C value and we have to know this condition. Then we can simply take this problem and we can simulate. Okay. One question is how will we go like start to solve this? So here he has something called he took this L-shaped plate.
Yeah.
Okay. And this can be easily done. So like you take this and you discretize into points. Okay. All right.
Yeah. Yes.
Yeah, and you'll connect them with the horizon. You'll save the initial neta value or zeta value. Okay, and I think he's applying force somewhere. I don't know. Yeah, here he's applying displacement. I think so this will start to move. As this moves, these points will also start to deform. And once this length increases to certain value, stretch value, we will see this is not in contact anymore. Like this bond will be broken. If this bond is broken, then it implies we will not consider that in the force.
I see. Yeah.
Force. So that is the logic of this. But this is very hard problem. This has damage. We don't want to do damage because we don't need to do damage in the first place. We'll just do just a simple deformation, elastic deformation. You can take this elastic gate because in elastic gate, this problem. If you look at the simulation. So this is how it works. First it is constant, then it will move, Okay. Similar in simulation, you can see, right? There's no break anywhere. There's no fracture like here. Right. So we can start with this. So because here there's no damage, there is only elasticity. We can consider this case as a first example to simulate. This is a physical validation. Okay. I hope you're following. Yeah. It's not that complicated. Yeah. I think yes. Really.
The thing is, once we introduce damage and all, right? So we have to have new, some time varying things as well. Like the material parameters themselves vary in time and all.
No, they actually don't. They don't actually matter. That's the beauty. Even though there is damage, the metal constant stays the same. But
the thing is, okay, I see.
That's the point. Just I think to introduce the damage, I'm sure he writes it here somewhere. Yeah. So damage is computed using this. So if the S value is less than S0, like S0 is a damage parameter. This is how we compute damage. Okay. Then there is no damage. If it is exceeds, like if say that this is the initial S, so I think the S0 he computes maybe somewhere like this. So as the particles start to deform, so once
so these are like state variables, right? That it does not explicitly occur in the governing equation, but there are some parameters which depend on it.
That is correct. So they're like the external parameters. So we at every time we will check if our bond Bond's S value,
Mhm.
which is S value is here, the elongation, right? Stretch, right? S.
Yeah.
If it is exceeding or not. If it exceeds, then we'll say it is damaged, and we'll simply break the bond.
Right. Yeah. Mhm.
So that's the point. This.
I see.
Yeah.
Mhm.
So I think that's it. So if initially you can just take some simple elastic beam like
Mhm.
this, okay, and
Yeah.
apply some force maybe here, and from the physics we know it will deform, no, like this. We can check that with analytical solution.
Exactly. Yeah.
And if
So
you're
this
so
can.
smart, then you can see how to. You can check some fracture as well and see if you have too much load, when it will fracture here or where it will fracture. That could be our
Yeah.
starting point. So I will
Mhm.
maybe next time we meet, I will just tell you how to write this in the code, or I will just write a simple algorithm and like whatever the for loop I wrote here. This thing, this for
Mhm.
loop, this for loop.
Mhm.
I will show you how to write this in a software, and how to do the basic like basic debugging, or like code development. Then I think that will be good enough. But we need to know. So I'm just saying if I'm missing anything more, like am I missing anything like in this? That's what I understood with the reading I have had with this paper. I realized this is all
Yes.
we need to know. Just that the C value is missing. I don't know how he's computing this. C value is here, C value is here as well. So I've searched for the C value, micro modulus. I couldn't find anywhere. So
Mhm.
that's the only value I think we need to. So the point here, the novelty of this paper is many people have already did SPH and dynamics coupling. So that's nothing new, to be honest. Okay, but the way he
Mhm.
pitched this paper is the way people pitch, like basically how they pitch the paper is. See, if you look, so the point is, I'll just tell you how he writes the paper. Okay, you already know, but I just want to, yeah. FSI, SPH is very much used. Okay, SPH is used, and dual S physics couples with Project Chrono. So next time, if we develop some software, we'll write Pi Peridynamics or Pi SPH
Mhm.
Peridynamics or something like that.
Mhm.
We'll put some name.
Mhm.
Okay, we'll say Pi SPH
Okay.
Peridynamics coupled with Pi SPH, or we'll say one integrated software we develop Peridynamics into Pi SPH.
Mhm. I see. I
Okay,
see.
and we will write like that. Then the point is,
Mhm.
so he says like, so peridynamics. So but SPH and other numerical methods are being coupled, but not SPH peridynamics. So here he says peridynamics is good for fracture problems when the forces are large enough for failure, because SPH can't
Mhm.
handle that. Okay. Then he says, see, already peridynamics SPH models are already there. You can see these papers, and also peridynamics SPH papers are applied. You can see here. That's what he says. But in this work, then what? It is already there. What I should do? Like what we are doing new. What he says is, I think he says some correction. He did some correction. He added some new correction terms. That's what he says here as well. I think. Sorry, just a moment. I'll show it here. So he
Sure.
has some
Sure.
highlights, but यहाँ पे highlights नहीं आया PDF में. Look,
I see.
he says corrections to PD model. ये पिछले लोगों ने नहीं किया. And this correction is not done by him. He bought this correction from Peridynamics paper, and he's
Okay.
adding it
Okay.
in
I see.
FSI.
Yeah.
So you understand, it's not nothing new. So he takes this Peridynamics paper corrections, he developed SPH, he couples these two. That's how he.
So he actually
Pitches.
modifies some volume finding, right?
Yes,
Looks like.
correct. Like near the free surface, like near the free surface, just this
Yeah.
near
Yeah.
free surface. I think.
Yeah. Yeah.
This is the this is how simple it is, bro. to start with dynamics. So you also have a look and see if you can find anything, say, about C. This guy didn't give any values of C, which is very surprising. I've seen all the like full paper I've seen, but I couldn't find. And even the live reviewers, they didn't say anything like boss C ka value kahin pe to nahi likha. He wrote C is microelastic modulus. It can be obtained from strain energy equivalence principle. But let us see if he has anything in the papers. Yeah, L यहाँ पे C value. Yeah, यहाँ पे भी नहीं है. Yeah, that's what. So C value is yet to be found. Which is, I don't know, like how would you compute C from strain energy equivalence principle? I don't know how you actually do that. So this is the first cut understanding of mine of this of fluid dynamics implementation. So once we are ready with this, the first paper we can write is open source software for fluid dynamics in Python. For fluid
Exactly,
dynamics.
and then have some good examples, right, as validation cases.
Yeah. So as you're saying, as part of your course. Okay. So I have downloaded one book as well, but I will not share it now as I can do it. But so as our software, first we'll write this. Then we also have SPH already implemented. So the way we write it is PySPH has good potential. This is why I'm implementing in PySPH, because PySPH mein I have DEM, SPH, multi-resolution SPH. I have done FSI in PySPH. I have done elastic solid bolids, elastic plastic in SPH. So इसमें है PySPH में. तो इसमें fluid dynamics implement करना is good. That's what we will say, and then we will improve. If you just say that I have developed this new code, some chota code hai, and develop kiya, then so many people will do it. No, he will not accept it. If you follow me, what I'm trying to say. That's how we pitch. So once we are done with that, so in your course or in our course, if you're recording and everything, then we can start with this. Then we'll do FSI coupling. Then first paper. Then next paper will be that one.
Yeah. So FSI coupling, then yeah. So in that will require like in the same framework or a different code, like
same
within the same software itself, right?
हाँ, develop हो गया. Then उसके बाद we will write PySPH coupled with fluid dynamics PySPH. So we will add, and there's one thing. उसके बाद we will add, because PySPH में there is also multi-resolution.
Yeah, multi-resolution MRE.
नहीं किया अभी तक fluid dynamics multi SPS से कोई नहीं किया.
हाँ.
Okay.
Yeah.
That will be easy now. That will be a first paper. That will like इसको बहुत citation मिल सकते हैं. We have to grab this opportunity like soon.
Right.
So as soon as we do this, like ये एक बार fluid dynamics implementation हो गया, then that's it. So multi resolution will take from our existing, like वो हमको develop करने की जरूरी नहीं है. सीधा लेंगे और सीधा same FSA developer, same examples. We'll write some 4 examples, and we will do those 4 examples to just keep on developing. Okay. उसके बाद since I have done DEM, I can add DEM to fluid dynamics. So that way we'll just write 4 chapters. A nice book, and we'll.
Right.
But first step I want us to do is, so next week we'll write the code Sida. Okay.
Yeah.
Only. We will not do anything fancy. We'll study together. I think that's a good idea. Is that right?
That's true.
I think that's a good idea. But in the free time, we can, when we are away, we can see that how we can resolve the issues we face while we're actually developing this code.
Yeah.
Okay, so this what I want to show. Shop sharing.
Okay. Okay.
Oh, so 1 hour हो गया क्या?
I don't know. I don't think so.
नहीं 47 minutes. नहीं 47 minutes में बात कर रहे क्या? Half an hour
Yeah,
हुआ.
yeah.
Anyways.
The thing is, they have not mentioned how long the recording has been, right?
Yeah.
So just.
So have you done any paid analytics in this few days?
No, no. Actually, I was just. I mean, this 2 days, no, because I thought this lecture would have been yesterday. And then I realized that I filled the form and I didn't recall the date myself.
Yeah.
So
Yeah. So I just looked at the paper, like नया paper क्या देखा था, and it was interesting. So I was like, okay, let me see, and I was able to understand, like, okay.
yeah, actually there is this APS coming, right? APS, this American Physical Society's March
It
meeting.
was every 6 months होगा ना या इसमें?
No, it happens every year.
Oh, it was 6 months before. That's what I remember. I'm happy they made 1 year now.
So the thing is, yesterday I just thought that I just felt like writing something, some abstract. So it is in.
Amul, it's playing well. Yeah, you should watch. Yeah.
Yeah, so I thought of writing some abstract. I started yesterday only.
You should.
Yeah. So
That's
this
important.
something.
That's most important thing. Ye paid analytics slowly we can do. So we'll just
Right.
meet like this. Whenever we meet, we'll do paid analytics. I think it's that a good idea. We'll read together.
Right.
I think that will be enough. So we don't have to just. So if you need some motivation now, like day अच्छा start करना है तुझे या फिर वैसा कुछ है. Okay, we'll just meet for an hour. We'll do some reading and coding, and
Yes.
that will give some ideas for us as well. And just we can just
Right.
get into our work as also.
Right.
That's right.
So what I did is I thought that it looks like shell theory, right, for magnetoelastic systems has not yet been explored properly.
Okay.
So the thing is, my guide, the thing is, he won't allow for APS meeting.
Huh?
The thing is, now he has presented our work, right, PhD work, in a conference in Japan. That IUTM conference. So now he just wants that we should write journal paper. Now no conference regarding the work that we do. So we are in the process of writing, as I had told you, right? We are in the process of writing. So I mean, it's going on slowly, but it's going on. But by this month end, we should have the first draft. That's what Sir has said that. So he's writing the first few sections, so like introduction, methodology, and he asked me to write the numerical part and answers results as well. So I had written theory as well, so I sent it to Sir, like the LaTeX file, so he'd be working on that. So the thing is, and if I say that, sir, I want to start something new, then he will just say, okay, but let's finish this work first.
Yeah. No. You. I don't think you should tell anything about paid dynamics to your professor.
Yeah. So what I'm doing is I have been part-time had interest in shell theories and all, right? This plate theories, shell theories. So the thing is, I think that if I put abstract somewhere, it will give a hard deadline that you need to work, but there is one target there. And if yeah, so it's closely aligned with my PhD work, because here also we are dealing with magnetoelasticity of slender structures, right?
Yes.
So little bit time, even in the lab, like in lab also, most of the time you don't know what you are doing, you're just sitting. So if and I'm just reading papers, I used to read papers on shell theories. I even got some codes by some professors at ETH, some Pedro Reis. He gave the COMSOL file. So I thought, okay, maybe it's better that I also explore shell theories, because being in slender structures, we should have knowledge of every area. Plate theories, very strong background in plate theories, shell theories. Ruds and ribbons we are already doing as right now as part of my work.
Okay.
So I just wrote one very short abstract, just some general idea, just throwing around. And I think that there is some what do you call huge rebate on people who are from India, right? Like from lower income countries, which
Yeah.
also include India as per the World Bank fact sheet. So India belongs to the lower income countries, or lower middle income, LMIC they call it.
Okay.
So they give a rebate of around 89%
Wow.
on the registration fee. So okay, I said okay, obviously I cannot get the money reimbursed. So 89% on $340, it brings down significantly.
Yes.
So
Yes.
around 90, just 10% of the original fees, around $35. So I think that $35 I can pay out of my pocket as well.
Yeah. True that.
With-
True that.
Without informing sir. Like I mean, once the work, if I'm able to do something, then I can show the results to sir. Thinking about doing some journals, etc. As then I can put in my PhD work as well, right? As research work.
Correct. Correct. Correct.
Yeah. So I was just
So
thinking
see,
this.
the one thing is,
Mhm.
if I'm sure, I'm definitely sure. Have you ever done something like this? Whatever I have presented, Avitak.
Never know.
Once you do that, no,
Um,
then I'm sure that you will start to think that मेरा जो shell theory है,
yes. Yes.
that stuff, how I can use peridynamics to handle. For example, I'm just searching for you
Sure. Sure.
shell shell theory, peridynamics. So in non-linear, so it's like shell theory is like plates, no plate theory. Is that what it is?
Yeah. Shell theory is like shells are curved plates.
J.N. Reddy, no?
Yeah. Yeah, of course. Yeah. Jen Reddy
J.N.
is, I
Reddy
think, one of the
published a paper in
yeah,
2016 on.
pioneers in this.
I'll just share it here. It's much better to do that.
Sure. Sure. Please do say.
Just sharing? No, not yet. Share screen. It's not broadcast. The hell is the... Yeah, it's broadcasting now. Just sharing?
No, no, please say. No, I'm just waiting for
Can
you
you
to
see?
share. Yeah. Not
Can you
yet.
see?
Not yet. Not yet. Not yet.
I think so. At least, yeah. Sharing, no? Can you see?
Yeah. Yeah. No, it's yeah.
See? Elastic shells. That's what you're looking now as part of your research. Yes, this paper.
Yeah. 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 16 years.
You
It's
read it
22
Texas A&M,
pages.
I think. Yeah, I read it in Texas A&M. पूरा इंडियन सी है
Okay,
मतलब
Jay,
शायद
yeah, Debashish Rai is, yeah, this
IISc
professor at
IISc से
ISC,
ही
yes.
wait he's from
Civil
which
engineering
department
department, yes. Civil engineering.
सिविल से है कुछ नहीं है देखो
I
तो
knew, I knew his student. He had a very hard time doing some work in peridynamics. He was an MTech research student, took 4 years.
because it's hard no because you should know this much only then you can implement and everything maybe उसको नया नया
Yeah,
किया
the thing
होगा
is, Debashish Roy is again not a very cooperative guide, so
वही
that's not the real.
see I explain it to you peridynamics was I say force come out for loop by loop you will see how easily you will get peridynamics I'm telling you dude seriously telling you
Uh-huh.
this will be easy
Uh-huh.
easy I can't tell you but at least it will be like very very fast because my experience I
Yeah.
had. So if you
Yeah.
look, so he says state based. He using state based. So state based is the
Okay.
next one, like second.
Yeah, the more general one, yes. Yeah.
Exactly. So he says
Yeah.
following the approach. So even that is
Passion, yes.
2000 में Schilling did bond based. 2007 में he did state based.
Yeah.
Okay. So
Right.
this we all know this stuff. Okay, we all know this. ये सब देखने की जरूरी नहीं है. Then here
Mm-hmm.
F is doing some F, and this is I think he uses in computation of the forces. No, and this is the equation, right? This equation 2.
Right. This is the one we are
See
looking
that
at.
we
This is
know
yeah.
this. So
Mm-hmm.
so like like I think couple of lectures before you presented, you wrote this equation.
Yeah, this is what we
Those
are
are actually
discussed, right?
state based.
Exactly.
They're not bond based. They are state based. So in state, yeah. So if you look, so he wrote those basic equations. Now he's bringing the classic shell modeling. Like how would you do classic shell modeling? So यहाँ पे will not have any pair dynamics. So it's like typical momentum equation, right? Surface based. Okay. Now what he will do is, now he will bring pair dynamics into this shell theory. So how will he do it? तो काइनेमेटिक्स लिखा उसने, सर्विस डिस्प्लेसमेंट, इक्वेशन ऑफ मोशन he will modify. ऐसा ऐसा है. If you know shell theory well, whatever it is, these are very easy to do. यहाँ पे जो तुम देख रहे हो,
yeah.
complicated because it has proof and everything. We don't need all this.
Clean style, yeah.
If you look at citations, much better to look at recent papers. See, you have dual horizon period dynamics. You see that?
Yeah.
Look here, thermomechanical behavior of shell structures. This is important. Okay.
Yeah, this Oterkus, I was going through. There are lectures by this Oterkus. Yeah. I'd share you the website. Yeah. I mean but the thing is, I never watched it completely. But the thing is, it seems that they have done a lot of work, yeah, in this area. Oterkus. I think there are two Oterkus. You see, I think they are a couple, I believe. Yeah. Okay. Because in the lecture, so one was male, the other was female. So yes.
Oh, I forgot. So
yeah.
You see, he has. So that's what I think. Here you are pro in this. Like kinematics of flat shells in classical quantum mechanics. I don't know. You should tell me if you know this or not. Like what he's talking about. Okay. So first he introduces basic. ये उसका क्या है? Like shell theory क्या है? Then he will get into paradynamics से क्या लेना देना है? How would you model that? Paradynamics. So since now first we are learning paradynamics. Like paradynamics क्या होता है? Like how we can do paradynamics. That's what we'll do first. So then you can see there are 100 areas, boss. So we can also do thin shell theory and FSI interaction. You understand? So at one, so you can also first learn paradynamics, then learn to do all this like shell theory कैसे develop करना है, ये सब कुछ you can learn. It's not difficult. Definitely not difficult. It takes some time, but you'll definitely be there. I'm looking at much more simpler problems, so that we are 23. If you see. Centrifugal middle see this. This is a good area. Look, same people, Zelda and Erkan.
Yeah. The Zelda and Erkan is. Okay, they are from Glasgow. Okay.
What's the name? Zelda? Oh.
And Ekra.
No. What is the full name?
Oterkus. Oterkus. They're, I think, Turkish, I believe. I don't know.
Yeah, true. Then UK, Stansted. I know this university. So you must have. I think no. These people only wrote that one. Paradynamics. The link I shared.
Exactly. That's what. Yeah, that's what. Yeah.
You see, this is Stansted, no? University of Stansted. Yeah, right.
Yeah.
How to see?
Yeah, I'll share you the lectures. Yeah, I just
public
the lecture.
For articles. No, I want to see who's the author of this website, bro.
This I know. This is more like some group.
Yeah, same dude, same. University of Salford. They are based at University of Salford. The link I sent you, they wrote very well.
Okay. Designed by Andrew Premchandar.
Same Department of Naval Architecture. No, third girl is also from the same place.
Okay, so they are maintaining. So they are maintaining, I believe.
She's doing that. So look, she's doing paradynamics. She does FSI, fractional mechanics. So paradynamics already has fractional mechanics. उसको क्या करना है? Multiphysics is like fluid structure interaction is multiphysics.
Yeah.
Okay. So then floating wind matlab same thing. FSI is
And the
also
thing is,
same.
offshore renewable energy, these are like topics for which you can get funds.
Exactly. Floating wind is same FSI. Offshore is FSI.
Yeah.
Final एनालिसिस छोड़ दो. FCFD तो same होगा. SPH CFD है. Mechanics of composite metals I don't know. And SPH she also wrote. This is my area. Like I have like all the most of the she wrote no predominantly organization. There is a group. They are dealing with the same group. And yeah, same people are doing curved elastic beams kaisa karna hai. So this is much simpler because since they cited cell theory, so the you don't know how it works. So first someone will publish on paper, okay?
Yeah.
Like Jane Reddy published this. उसने बहुत theory लिखा है उसमें.
हाँ, Jane Reddy, yes.
It was in 2016. Now this is in 2023 October. Okay. Now the theory will come and come. We'll only see equations now. Look, only equations we'll see. What?
But she has done, okay, this is done for a beam, right? So beam should not be that complex. So what they have done exactly? Can we just scroll down?
So these are the classical equations.
Yeah. Right. Tangent.
You are following. Just let me know if you're not following anywhere. And I don't know what exactly to look here. She wrote some equations too. First, she has this energy equation. Maybe to compute the C value, they use this energy. So he has
right.
Typical period introduction, horizon, W value. Yeah. Then this equation 14 is also like very much same.
So these are that, okay, the strain energy density.
Work. It's not easy, bro. I have to know some more stuff. So ultimately,
actually this formulations I have used right in my right now. I mean,
oh, is it?
In my yeah.
Okay, that's great.
So yes.
That's what. So if you know period dynamics, how to use, like in the next sometime, if you know how to use it, code it, then you take the formulation, period dynamics में डाल, निकाल बाहर, बस कुछ नहीं करना है. Then she's doing some simple problem, simple support problem, clamped beam.
Yeah, exactly. Which method she has used? Which series expansion?
I don't know that. I don't know anything about this stuff actually.
A mesh-free approach discretized with coordinates. The thing is, this becomes just a 1D problem, right? I mean, 1D materially, but 2D in deformation.
Correct. Yeah, this one.
Yeah.
See, the point is, if you think you can understand the theory, then you are there, bro. You are like, it's easy for you. Not at all. Spread dynamics will take care. Look, even here, elastic plastic is introducing elastic plastic for spread dynamics. Not difficult.
Yeah. So I think that you could just share that paper, right? By that what do you call the one that we just saw. I just want to see what they have done.
This one, right?
Yeah, this one, yes. And it seems it's so recent.
It is. That's why we are looking at recent papers only. But target is to recent only. How to do that? Yeah. So what? So shell theory. We learn some period dynamics, and we are there.
Yeah, yeah, that's true.
So there's so many areas. So once we do the PISPS, then you can slowly go here, there, and so
ultimately, because the thing is, ideas are very closely this one, right? Related ultimately. I mean, as you mentioned, the SPH and
So I think one more thing I usually I learn to learn physics is usually people love books, but they like fluid mechanics. But say I want to learn surface tension, okay, I'll go in the point of view of SPH. Like SPH ने surface tension कैसा किया?
Yeah.
That's how I attack anything. Because I know SPH very well, like क्या है boss का यहाँ पे force है सब कुछ. So since you know shell theory, once you know period dynamics, once you understand period dynamics, then whenever you look at anything new, you're like, okay, ऐसा इसने model किया है ये final equations है period dynamics में, then you will easily understand, okay, ये shell कैसे model किया, then how he computing forces, like the main equation.
Mm-hmm.
Even in there, she did state based. We can do bond based. Bond based. We can look at, and that's what. So you are going more into physics side. That side nobody touches. Everybody touches some numerics. So she said,
Yeah.
I'm doing some curved beam. You'll say, I'm doing some. You'll do your area, like to some structure.
Yeah.
But it's a good area. I think I can see that. I actually see that.
Mm-hmm. This the thing is what they have done is they must have used that Euler-Bernoulli assumption and all, right?
Oh.
So so there is space for doing, say, for Timoshenko theory, Timoshenko beams, and all that.
So there's something. This guy called Nayak, I think. एक बंदा है हमारा IIT बॉम्बे में प्रोफेसर स्ट्रक्चर्स aerospace structure professor. He's not Nayak, but I remember him as Nayak. You can see if you can get alumni or something. तुझे इनके नायक पता है? वो इनके नायक नहीं है यार. So what he does is he usually deals with deformation of structures, elastic structures.
Okay.
Okay. So he will consider additional terms. So जो भी नया बंदा आता है, they'll do something. They will consider some more additional term. Like I don't know what exactly that is also. They'll rerun the examples and they'll consider new results and they'll publish. That's what they.
So I'll just stop recording so that we can just have some conversation.
Long back, no.
No.
What?
Don't worry, I can edit that part out.
Which part? So you have to be careful with this. Just edit out. Just make sure. That's why I asked. Have you stopped recording? You stopped recording long back, man.
Okay.